So we're going to shift gears a little bit right now and talk about ways to measure energy expenditure, and this is going to be related to oxygen consumption also, at least for the most part. So there's different ways to quantify energy expenditure, and so these are known as calorimetry. So calorimetry is basically when you determine how much energy is being transferred. So there's direct and indirect. So direct calorimetry is where you're actually measuring how much heat is being produced uh, at rest or during exercise. So it's based on the concept that all metabolic processes produce heat as a byproduct. And so this requires really expensive equipment, and usually either someone is in a metabolic chamber is the term that's commonly used, but it's basically a room that can detect temperature changes. And so the amount of heat that the body's giving off changes the temperature of, usually it's some type of water or fluid flowing around the chamber. And that temperature difference can be quantified. And so heat, when you measure heat, that is direct calorimetry. Indirect calorimetry actually is where you measure oxygen consumption. And there's two different subcategories of indirect calorimetry: closed and open circuit. So closed circuit spirometry is where you would actually breathe in 100% oxygen, and then the gases that you exhale are analyzed for content. So it's called closed circuit because it's a closed system, and you're breathing from an oxygen chamber, and what you're exhaling goes back into that chamber, and you can quantify the difference. So that's closed circuit. Open circuit also measures oxygen consumption, but it's a little bit different. You breathe in room air, and then only what you exhale is quantified for the expired gases. So it's open circuit, meaning that you breathe in from the atmosphere, and only what you exhale goes into and some type of analysis. So kind of big differences between direct and indirect. Direct calorimetry, which is thought to be the most accurate, measures how much heat's given off. Indirect, oxygen consumption. So indirect is based on the concept that most of our metabolism is due to oxidative metabolism, because it really doesn't tell us a whole lot about anaerobic metabolism, whereas direct calorimetry can. So that's a big difference, and this is why direct calorimetry is thought to be more accurate. So which one's best during exercise? Generally speaking, direct is hard to do during exercise because you just have to be really careful. If you were exercising, one, you would have to be exercising in a metabolic chamber. Then the exercise device itself is going to give off a little bit of heat too, so that would have to be taken into account. So not commonly done. Closed circuit indirect calorimetry is not heavily used during exercise also, just due to the volumes of air that are inhaled during exercise. So if you're breathing in from a limited oxygen chamber, then it's not going to be able to handle like the large volumes of air that are inhaled during exercise. And so that leaves us with open circuit, which is most commonly used during exercise. And that's because you have an unlimited amount of air you can breathe in, and only what you exhale goes into an analysis system. So open circuit, based on the concept that we have a fixed amount of oxygen and CO2 in the atmosphere. So those numbers, 20.93 oxygen, 0.03% carbon dioxide, that's pretty much standard regardless of if you're at sea level or high altitude. So altitude only really affects the pressure, but the percentage will be the same. Some people around will say 20.94, so it's either 20.93 oxygen or 20.94. We'll go with 20.93, but CO2 0.03%. The bulk of the rest of the atmosphere is nitrogen. So when you exhale, so that's what you're breathing in during open circuit, and then what's exhaled goes into an analysis system. And so as you could imagine, the oxygen and expired air is going to be less than this, because your body's going to consume some of it, and that difference is going to represent the oxygen consumption. And the CO2 will be the opposite. So if you breathe in 0.03, you will exhale more CO2 than that, because these metabolic processes produce carbon dioxide as a byproduct. So even the numbers exhaled are going to change, and that's constantly changing depending on what you're doing, rest versus exercise. But to give you an idea, probably be around 15% exhaled oxygen and about 3 to 4% exhaled CO2. All right, units of VO2, we're going to refer to them as either being absolute or relative. So earlier when I showed you the VO2 max norms, I said they were in units of milliliters of oxygen per kilogram of body weight per minute. That's a relative terms because it's relative to body weight. And so this is what it'll look like, milliliters per kilogram of body weight per minute. So those VO2 max numbers or norms are always put in relative units just because you can compare yourself to people with different body weights. You can also report VO2 in absolute units, which is just liters of oxygen per minute, so liters per minute. It does not take into account body weight, so it's a little bit different. So you can convert back and forth between the two, and you should be able to do this with relative ease, obviously with the use of a calculator. But if you wanted to convert absolute, you would just need to know absolute to relative. You would just need to know the body weight. So, for example, if you had 3 liters per minute of absolute VO2, and you wanted to convert that to relative units, and if you know the person's body weight is 70, you could just do the calculation. My preference for this, just to make sure you don't mess it up, because you always want to make sure your numbers make sense. So 42.9 sounds like an acceptable relative of VO2. If I got something like 0.4, I would know that was off. So you just kind of have to have an idea of what's normal, what's not. But nevertheless, I would do this in 2 steps. So the easiest thing to do to make sure you keep everything straight is convert the liters to milliliters first, and that's the easy conversion. So 3 liters, 3,000 milliliters, and then divide by 70, and that should give you that number. And then you should be able to work backwards. If I give you relative and ask you to put it in absolute terms, you should be able to do that also. So this will be important when we start doing these metabolic calculations that we'll get to shortly. So we also have a distinction between what we call gross and net oxygen consumption. So gross VO2 or gross oxygen consumption is basically your oxygen consumption that would be measured. So if I'm walking down the street and I measure my oxygen consumption or estimate my oxygen consumption or somehow assess it, and let's say it's 10 milliliters per kilogram per minute, that's gross, because not only does that take into account the oxygen consumption that's associated with walking, but it also includes my resting metabolism. You can subtract out your resting metabolism if you want, and so that would be the net VO2. So net VO2 is oxygen consumption in excess of the resting metabolism or resting VO2. So back to that example, if I'm walking and my oxygen consumption is measured at 10 milliliters per kilogram per minute, that would be my gross. And let's say I know my resting oxygen consumption is 3.5 milliliters per kilogram per minute. That means my net VO2, which is associated with that walking, would be 6.5. So if you just subtract out your resting metabolism, that gives you your net VO2. That's useful when you want to see how much energy you're expending due to the exercise bout itself. Because if you just look in gross terms, that also includes your resting metabolism. So net VO2 equals gross minus resting. So we'll talk about resting VO2 numbers in a few minutes. But before we do that, I want to talk about something called the respiratory quotient. And you'll see a similar term called the respiratory exchange ratio. So basically the respiratory quotient is the ratio of the volume of carbon dioxide produced to the volume of oxygen consumed. So it looks like this. So we exhale a certain amount of CO2, we consume a certain amount of oxygen. If we look at that ratio, it gives us this quotient. And it's going to be between 0.7 and 1 for the most part. So this is an important ratio because it can give us an idea of what fuel we're utilizing, whether we're using fat or whether we're using carbohydrate. So the idea is that carbohydrate, fat, and protein require different amounts of oxygen to metabolize. and thus they give off different amounts of CO2. So if you calculate this ratio, it can give an idea of which one you're using. So if we look at this chart, and I kind of circled the numbers I think are relevant here, but carbohydrate, glucose or glycogen, I just circled glucose. This is about how much oxygen you need to utilize to metabolize a gram of carbohydrate. So 0.75 liters of oxygen per gram of carbohydrate. In return, this is how much carbon dioxide is given off when you metabolize glucose. So the respiratory exchange ratio would be this divided by this. So CO2 divided by O2. And as you can see, that's going to give us a respiratory quotient of 1. If we look at glycogen, exact same thing. So it's safe to say that if we are utilizing 100% carbohydrate, that our respiratory quotient will be 1. I'm going to jump over here to fat, because we know fat's utilized a lot also. So this is how much oxygen you need per gram to metabolize it. This is how much CO2 is given off. So the respiratory quotient would be CO2 divided by O2. You can see that this is going to be less than 1. So 1.43 divided by 2.02. And so most individuals, we kind of round off a little bit. We'll say fat is around a respiratory quotient around 0.7. And that's generally what most people would agree on. Protein, you can see it's also going to be less than 1. So generally people say it's about 0.82, somewhere in there. Now, key point here, I'm going to bring this up again. We know protein, from our previous discussions, protein's not ever really a major source of energy transfer. So if we see an RQ of around 0.8, generally what that means is we're using a mix of fat and carbohydrate versus we're using mostly protein. So you got to kind of keep some common sense about this too. So just because it may spit out a RQ of 0.82, it doesn't mean you're using 100% protein. More, I mean, realistically what's going on is just a mix of carbohydrate and fat. So accepted RQ values, carbohydrate 1, and we clearly saw that. Fat 0.7, we just round it to that. It's around 0.68, I believe. Most people would agree on, and then protein 0.81. And so, like I said earlier, we often report these as a non-protein RQ, which basically means you ignore it. So if you see an RQ of 0.81, it doesn't mean you're using 100% protein. It's just a mix of carbohydrate and fat, assuming that the person's in a normal metabolic state. So this other term that you'll see is the respiratory exchange ratio, or RER. It's the same thing. So there is a difference, but the calculation is exactly the same. So the way I explain this, and I think it's the only way I can explain this, is that the respiratory quotient that we just talked about is assumed to be at a cellular level. So let's say within a muscle cell, the muscle cell is consuming some oxygen, it's producing CO2. If you measured it right there at the cellular level, that's an RQ. However, that's not realistic in most cases. So what we do is we measure it at the ventilatory level, at the level of expired gases. So we can, using indirect calorimetry, for example, we can determine how much CO2 is being given off and how much oxygen is being consumed. And if we use those numbers at the ventilatory level, it's now called a respiratory exchange ratio. So other than that, it's exactly the same. However, there are situations where the RER, the respiratory exchange ratio, can go over 1. And so that will never happen for RQ. So basically what's going on here is that something is changing between the cellular level and the ventilatory level that's going to alter our levels of either CO2 or oxygen being consumed. And as you're going to see, it's the CO2. So decreased pH, think of higher exercise intensities, you start to get more acidity. And so what your body does with the hydrogen ions when that happens is your body has these buffer systems that try to maintain a given pH. So even though pH drops a little bit, your body's fighting that and trying to maintain a set pH. So one of the buffer systems is the bicarbonate buffer system, which you may have seen before, but this is it. So when you get these hydrogen ions produced, maybe high intensities of exercise, you have this bicarbonate ion, HCO3, which binds to it, and you get this, which is carbonic acid, which quickly dissociates into water and carbon dioxide. So you see where this is going. So due to this buffer system, you're getting some excess CO2. Now this occurs in the blood. So this is after the cellular level where the CO2 is actually produced due to metabolism. So this CO2 coming from the buffer system is non-metabolic CO2, meaning it did not come from metabolism. So if you think about what that's going to do to the RER, all of a sudden you're getting this excess CO2 coming from this buffer system. It's going to drive this number up. So you're actually going to get respiratory exchange ratios that can exceed 1 during high intensity exercise. So during a maximal test, it's not uncommon to see RERs of 1.2, 1.3, and that's due to this buffering capacity of your body. And then also hyperventilation. So if you're hyperventilating a lot during high intensity exercise, you tend to exhale a lot more CO2 than is actually coming from metabolism. So these two things, hyperventilation and the buffering of these hydrogen ions, lead to the respiratory exchange ratio being greater than 1 during high intensity exercise. The respiratory quotient will never go over 1, theoretically, but the respiratory exchange ratio will. And that leads us to caloric equivalent of oxygen, which is kcals of energy produced per liter of oxygen. So this is a fun way to look at efficiency of the substrates that we're utilizing. So how much kcals can you get per liter of oxygen using fat or carbohydrate? So in other words, the energy you're getting from these substrate varies, or they require different amounts of oxygen basically to get energy. So these are the numbers, and you don't necessarily need to memorize these, but just know that this is about what fat is. This is about what carbohydrates. A lot of people round this off to 5. Fat 4.7 is fine. But when you look at how much energy you can get per liter of oxygen using fat versus carbohydrate, it becomes clear that carbohydrate is a more efficient substrate. So carbohydrate is kind of like an efficient car, whereas fat is almost like a gas guzzling SUV. So back to our discussion about like shifting to carbohydrate during high intensity exercise, this comes into play because it makes more sense to use something that's efficient when you need ATP really quickly. And carbohydrate, looking at these numbers, is a lot more efficient than fat. And so carbohydrate's a more efficient fuel when you look at the caloric equivalent of oxygen. All right, so we can also use that caloric equivalent to estimate energy expenditure from oxygen consumption. So in other words, that gives us the caloric equivalent of oxygen gives us a nice conversion between oxygen consumption and kcals. So when we do this, if you want this to be accurate, obviously you would want to know the exact percent of carbohydrate versus fat that you're using, and thus you would need to know the respiratory exchange ratio, or RQ. However, that's not realistic in most cases, so we just use a caloric equivalent of 5 in a lot of cases. You could use 4.85 if you want to do somewhere in the middle, and some people do that, but 5 is a nice round number, so we're going to go with the caloric equivalent of 5, and there is justification for doing that. So we are kind of assuming that we're using mostly carbohydrate. So an example of how you would do this: convert an oxygen consumption of 2 liters per minute to kcals per minute. So if we're going to assume a caloric equivalent of 5, all we need to do is this. So this is our absolute VO2, 2 liters per minute. Multiply it by 5 kcals per liter. That's the standard here. That's the conversion. And we get 10 kcals per minute. So, and the liters obviously cancel out. So we can now say that an oxygen consumption of 2 liters per minute is equivalent to an energy expenditure of about 10 kcals per minute. So using that that conversion factor of 5. So this is a good thing to do, because one of the things we're going to be expected to do shortly is convert VO2 into kcals per minute. And we're going to always assume, at least in this class, that there's a caloric equivalent of 5. And we're making an assumption that we're using mostly carbohydrates, but that's commonly done, so we'll go with it. Now, one thing to consider also, if you had to convert a relative VO2 to kcals per minute, you would need to first convert that relative VO2 to absolute VO2 and then do this. So another thing to consider is when you're trying to get the caloric cost or energy expenditure of a given activity, you generally want to use net VO2. So back to that example of walking and your VO2 is 10 milliliters per kilogram per minute. That would be gross VO2. But if I really wanted to see what the energy expenditure was due to that walking, and not including my resting metabolism, I would subtract out my resting metabolism just to see how much energy is being expended in excess of my resting metabolism. So you generally want to use net VO2. When questions on an exam come up, I generally make them relatively clear as far as should you use net or gross. All right, metabolic equivalents, or METs. You probably heard the term MET before. So one metabolic equivalent is your resting metabolism. So obviously it's going to vary a little bit between different individuals, but we just generally say one MET is your resting metabolism, and there is a conversion to oxygen consumption. So before we get to that, 2 METs would be 2 times your resting metabolism, so on. 5 METs, 5 times your resting metabolism. So 1 MET is equal to about 3.5 milliliters per kilogram per minute, and that's why in that example I kept saying my resting metabolism is about 3.5 milliliters per kilogram per minute. Not everybody's is going to be 3.5, but it's a nice kind of estimate of resting metabolism. So this is kind of the understood kind of default resting metabolism. 1 MET, 3.5 milliliters per kilogram per minute. In reality, it might be 3.2. It might be 2.5. But 3.5 is a good estimate that we tend to go with. So 10 METs, if we wanted to estimate VO2, would be a VO2 of approximately 35. Just multiply 10 by 3.5. Now, if we were working at 10, just another example, let's say you're working at 7 METs. So your 7 METs is the intensity. If that was gross metabolism, if you want a net metabolism, that would be 6 METs. So you just subtract 1 MET would be your resting metabolism. So it relates to gross and net VO2 also. All right, moving on, we're going to finish up here talking about metabolic calculations and then exercise economy. There are validated metabolic equations that can be used to estimate energy expenditure based on exercise workload. And what I mean by workload is, for instance, treadmill speed and grade. Also, if you're on a bike exercising, the power output or the work rate that you're producing on a bike. You can use that to estimate how much energy you're actually expending. And really what we're going to do is estimate VO2 first, and then as we've seen, we can convert that VO2 to kcals per minute. So all these equations are going to give relative VO2. And to get energy expenditure, like we said, if we get relative, we can convert that relative to absolute VO2, and then we can get to kcals by using that caloric equivalent of oxygen, which we're going to assume to be 5. All right, so also, like I said earlier, if we're looking for energy expenditure, generally we're going to use net, where we kind of subtract out the resting energy expenditure. And I'll try to make that as clear as possible which one you need to use on any example. So the equations we're going to look at, these are all developed or produced by the American College of Sports Medicine. And there's a walking equation, a running equation, and a cycling equation that we're going to talk about. So for the walking equation, it's accurate for these speeds. It's validated in these speeds. It's going to give relative VO2. There's different components. The running is going to be the same. So oxygen consumption has a horizontal component, a vertical component, and a resting component. So that resting component is always going to be the 3.5 of a resting metabolism. As far as the vertical, that's if you're walking up a hill. And horizontal is basically the speed that you're walking. So this is the equation. You don't have to memorize this. It'll be given on any exam. But VO2 equals 0.1 times speed plus 1.8 times speed times grade plus 3.5. You see that's your resting component. The speed has to be in units of meters per minute. And the grade has to be percent grade as a decimal. And so the conversions, since we're used to miles per hour, 1 mile per hour is equal to 26.8 meters per minute. And then percent grade should be, so it's 5%, it would be 0.05. All right, the running equation, so it's valid for speeds over 5 miles an hour. Set up exactly the same. It's just the constants are different. So VO2 is 0.2 times speed plus 0.9 times speed times grade plus 3.5. Same thing. Speed has to be in meters per minute. Grade has to be as a decimal point. So a quick example. So calculate VO2 for running 6 miles an hour up a 5% grade. So first thing we would do is convert your miles per hour to meters per minute. Then our percent grade to a decimal point, and we put in there's our equation. Notice I'm using the running equation because this is a running example. Put in our numbers here, and what we're going to get is this. So VO2 is 42.9 milliliters per kilogram per minute. If we wanted to, let's say if you wanted this in METs, we would just divide this by 3.5 and that would give us METs. We could also, like I said earlier, convert this to absolute VO2 if we knew the person's body weight and then get kcals per minute. There's a lot of options here, but first and foremost, we're just getting VO2. All right, the cycling equation, we'll call it the leg ergometry equation, is a little bit different. So you have to calculate work rate or power in units of kilogram meters per minute. And sometimes power is given in watts. Watts will not go into these equations, so you would have to convert it to kilogram per meters per minute. Here's the conversion. So 1 watt is equal to 6.12 kilogram meters per minute. So work rate or power is due to these things. So resistance, that's the force that you're pedaling against. The distance, which is going to be consistent for us, it's the distance that the flywheel on the bike would go during 1 revolution. And then the frequency, or RPMs, that's the revolutions per minute of the pedals. So basically the cycling cadence. So resistance, force setting, frequency, the pedaling frequency, distance, how far it goes in 1 revolution. For our purposes, we're going to assume a Monarch leg ergometer, which is the most common laboratory ergometer, and it has a distance of 6 meters. So here's the equation, and it's valid between these power ranges. VO2 equals 1.8 times work rate, that's the power, divided by body mass, which is just body weight in kilograms, plus 7. 7's our constant. And so this is where all those constants are coming from. You really don't need to know this, but if you're curious, 1.8 oxygen cost of cycling against the resistance. That's why you have to multiply that by the work rate. 3.5, there is a resting component here, so half of the 7 is due to the resting component, the resting metabolism. And then the other 3.5 is the cost of cycling with no resistance. So just pedaling against no resistance has an energy cost. So putting this all together, you can see where this is going. If we want to use this equation, we have to calculate the work rate first. The work rate came from this. All right, so if you know the resistance, the distance, and the frequency, then you can calculate the work rate, and then you can put that into this equation, and you would just have to add in the person's body weight. So, example. So what's the oxygen consumption for an 80 kilogram person cycling on an ergometer at 50 RPMs, 2 kilogram load? 2 kilogram is the resistance. So the first thing we'd want to do is calculate the work rate. So 2 is the resistance, 6 is the distance, that'll be constant for us, 50 is the RPMs. That gives us 600 kilogram meters per minute. We put that into the equation. Here's our equation. So 1.8 times 600 divided by 80. 80 is the body weight plus 7. We get that, and there we are. So the oxygen consumption is 20.5 milliliters per kilogram per minute. Remember, if we want to convert this to METs, we just divide by 3.5. Alternatively, we could convert this to absolute units and then convert it to kcals per minute, depending on what a question is asking. Yeah, so you'll get a lot of examples of this. I'm going to give you a worksheet with a lot of practice questions like this, so you're comfortable doing these calculations before the exam. All right, so remember, if caloric expenditure is desired, we'd use net VO2. So, for example, if 70 kilogram person's exercising at a VO2 of 30, and that, or let's say you got 30 from one of those equations that we just did, and we wanted to get caloric expenditure, we would get net VO2 first. So 30 would be the gross VO2. Subtract out our resting, which is 3.5. We get a net VO2 of 26.5. And then we would convert that to absolute units. And you can see my calculations here. So converting that, given the person's body weight as 70 kilograms, get 1.85, 1.86 liters per minute. And then to get kcals per minute, we multiply that by 5, because we're always going to use this 5 kcals per minute, 5 kcals per liter as our caloric equivalent. And so at this intensity, the person has a net energy expenditure of 9.3 kcals per minute. So what we could also take this a step further and see, what if they did this for 20 minutes? How much energy would they expend? And this could be useful if you're trying to calculate how much energy you need to expend to reach a given goal. So basically multiply that 9.3 kcals per minute times 20, you get 186. So if this person exercised at that intensity for 20 minutes, they would expend 186 kcals. All right, what I'm going to finish up with here is exercise economy. And so economy in this context refers to the oxygen consumption required to perform a given amount of work. So basically work being done divided by metabolic cost. So generally speaking, the lower oxygen consumption is means a higher economy. And so if you're able to run at a certain speed and use less oxygen, that means you're more economical. So in this graph right here, what you're seeing is one person who came in for 2 visits, first visit versus second visit. They measured oxygen consumption while they ran at these different speeds. And you can see out in their second visit, they were much more economical because they did the same amount of work using less oxygen. And the units are a little bit tricky here because it's not in the same units we did, but it doesn't matter because we're just looking at what's higher than the other. But their second visit, they were much more economical. They did the exact same amount of work with using less oxygen. And that we're assuming that this person underwent some type of training program, so their body became more efficient and more economical. So how does this relate to potential pathological conditions or any type of injuries that may occur? So first of all, how does the movement economy influence the accuracy of the metabolic equations? So those metabolic equations and calculations that we just did, they're assuming a lot. So they're assuming that the person has an average movement economy, But you could imagine if someone had a really poor economy of movement, that the equations might be off a little bit. Or if they had a really great exercise economy, the equations might be off a little bit. So those equations were validated in people, just healthy adults. So anything that would alter your movement economy could alter the accuracy of those equations. So as far as what populations might have a significantly altered economy, any condition that impairs movement might. So any any population you might see in rehabilitation programs, like maybe people with multiple sclerosis or who've had a stroke, their movement economy may be significantly altered due to their movement pattern. So things like using a walker or a cane is going to impact movement economy. So these are all things to consider if you're trying to estimate energy expenditure based on those metabolic equations.